Mechanism designed without money. Despite the impossibility results on general domains, there are some classes of situations in which there exist interesting dominant strategy mechanisms. While some of these situations and the resulting mechanisms involve the transfer of money, we examine some that do not. Specifically, we analyze problems where agents have single-picked preferences over a one-dimensional public policy space, and the problems where agents must match with each other. Introduction. The Gibbard-Satterwhite theorem, Theorem 9.8, is a Procrustean bed that is escaped only by relaxing its assumptions. In conjunction with the revelation principle, Proposition 9.25, it states that on the general domain of preferences, only dictatorial rules can be implemented in dominant strategies. If the range contains at least three alternatives, in this chapter, we escape Procrustes by examining dominant strategy implementation on restricted domains of preferences. In most applications, it is clearly unreasonable to assume that agents' preferences are completely unrestricted, as was assumed in the voting context of Section 9.2.4. For instance, in situations involving the allocation of goods, including money, one can safely assume that each agent prefers to receive more money or other goods. As can be seen in the following chapters, the ability for agents to make monetary transfers allows for a rich class of strategy-proof rules. Nevertheless, there are many important environments where money cannot be used as a medium of compensation. This constraint can arise from ethical and/or institutional considerations. Many political designs must be made without monetary transfers. Organ donations can be arranged by trade involving multiple needy patients and their relatives. Yet monetary compensation is illegal. In this chapter, we focus on a few examples of just this kind. Before proceeding with the examples, we formalize the idea that dominant strategy implementation is a weaker concept on restricted domains of preferences. In general, a decision problem can be described by these parameters. A set of agents n equals to the set 1 to 3 until n, a set of alternatives A, and for each agent I in n, a set of potential preference relations Ri over the alternatives in A. The Gibbard-Satterwhite theorem, Theorem 9.8, applies, for example, when each Ri is the entire set of linear orders on A. An allocation rule is a function f which maps from the product of Ri to the range of A, mapping preferences of the agents into alternatives. It is a strategy proof if its use makes it a weakly dominant strategy for agents to truthfully report their preferences. See section 9.4. We observe the following principle. Consider two decision problems. In A, R1, R2, and so on until Rn, and in A, R1 prime, R2 prime, and so on until Rn prime, where Ri prime is a subset equals to Rn for each I in n. Suppose f which maps from the product of Ri to A is a strategy proof rule for the formal problem. Then the restriction of the function f to the product of Ri prime, namely f under the condition of the product of Ri prime, defines a strategy proof rule for the later problem. The proof of this is straightforward. On a smaller domain of preferences, strategy proofness is easier to satisfy because it imposes strictly fewer constraints. This simple observation justifies the search for reasonable, or at least non-dictatorial rules for decision problems involving smaller domains of preferences than those that yield the Gibbard-Satterthwaite theorem. In section 10.2, we analyze a problem involving a natural domain restriction when agents vote over one-dimensional policies. It is one of the canonical public good settings. Ri equals to Rj for all ij in N, in which interesting strategy proof rules can be obtained. The analysis here is illustrative of the approach used to characterize such rules in other environments. In section 10.3 and 10.4, we analyze matching problems, as opposed to the previous setting. These problems have the feature that each agent cares only about his own private consumption. That is, each Ri contains only preference relations that are sensitive only to certain dimensions of the alternative space A. Hence, Ri not equals to Rj whenever I is not equal to J. These are examples of what are called private good problems. Two kinds of matching problems are analyzed, demonstrating the limits of what can be implemented in dominant strategies in such environments.